Okay, so thanks everyone for joining. Previous lecture session, we were talking about pre-training. We all know what is pre-training. Pre-training is a situation where we take our data set and then we choose a training strategy, which can be either encoder or decoder or encoder-decoder, and then we train a language model from scratch. And then when we train a language model, we can use that language model, to do fine tuning or downstream tasks. And that language model we create from scratch is sometimes called a Bayes model. Bayes model, yeah. That is what we call pre-training, and we saw a lot of other stuff in terms of pre-training. You're gonna have a lot of, you have open source model, such as GPT. We have Llama. We also discuss what is scaling law. Scaling law means that when you train your language model with more data, with more training time, it, performs more better. We also discuss about, open source by closed source Axe models. So open source models are long models that, basically they do have, many things open. For example, the weight of the model, because the inference code, training code, the data, everything is open. That's what we call open model. So some of the open model we know there is some Llama, Mistral, Pen. All these are open models, right? Meaning that you can just take them, fine tune them, or do whatever you want. And this is how science progress. When we have open models, we can explore, we can iterate, we can do many things. We also have closed models, closed model, such as, okay, these are also other models which are open model, such as Code, Code Llama, DeepSeek. All these are for doing coding tasks, for coding tasks. These are math models specifically trained on math data set. For example, this DeepSeek math and everything. We have science models. For example, these are language model trained to perform more on scientific domain. For example, you can see here, we have one called Galactica. It can work on many stuff like, DNA sequence on scientific stuff. That's for open model. We also discuss about closed models. For example, GPT-o, these are what we call closed model because you cannot get the code, you cannot get their data they use to train the model. Everything is hidden. Mainly because this is something companies working on. They need to get some money. Gemini, they are closed model. Cloud, they are all closed model. So this is what we discussed last week. Today, what we are going to discuss is what happened now after you train your model, right? After you train your model, what happened? What I mean by what happened is that maybe, for example, you train your model, and then it turns out that after you train your model, um, it turns out that the model does not work well. For example, in terms of safety, for example, you take your model, you do a pre-training. What we talk about, you did a pre-training, you train all, but the model is not safe. Meaning that, for example, when you ask the model, give me a step to kill somebody, it may give you a step by step how to kill your friend, right? So it's not safe. So one approach we say is called post-training. How can you, after training your model, how can you instruction fine-tune your model, using what we call instruction tuning, data set, and OSFT, or alignment? There is something called alignment, LLM alignment. How can you align your model so that it doesn't work, anyway, anyhow? So let's quickly look at what does that mean. So the first thing we talk about fine-tuning, we already talked about, let me just wait. Is this the, okay. Maybe just give me, excuse me, I want to check if this is the slide I wanted. Okay. Okay. Just excuse me. I think this is not the updated slide I want to share. Just excuse me. I have the updated slide. Um, um, excuse me. I have the updated slide because I think I did update the slide. And therefore it should have some update in it. Just yeah, I know. Okay. Yes. Okay. So um so I got the updated slide. Let me share screen, then we can see. All right. Okay. All right. Can you see my screen?
Yes.
Okay. So the screen. View which one to read as a slide. Let me see this. Is it it's supposed to know? Okay, maybe like this. Oh, okay. Okay, can you see that now?
Yes, sir, you're,
Okay.
you're visible.
Okay. So the only thing I think maybe is it on. Okay, let me see. Okay. Anyway, I can manage to do that. Okay, so as I was talking about oh, this is pre-training, right? Oh, oh, okay. Oh, okay. So this is not the post-training. Let me download the post-training. Just give me a second. Sorry for the miss. Yeah, it's pre-training. Hmm. Okay. Okay, can you see the screening? Is it post-training? You can see. Is it post-training?
Yes, we can see it. Post
Is
training
this
for large language models.
okay? Okay. Yeah. So this is my this slide. Okay. So as I was talking about before was we did pre-training, where in pre-training is something that we take a huge amount of data. we train our language model, and that language model we create, we call it base model, right? So for example, now you take a huge amount of data, very huge amount of data for Hausa, and you train your language model. Maybe you have Hausa VAT, right? That language model, that thing you did is what we call pre-training, and you now have a language model or something like that, and we call it base model. But the thing is that base model may have several issues. One of them, for example, is that your language model may be harmful in the sense that one example is that you may ask your language model, how can I skill somebody? If it is generative model, it may give you step-by-step guide, right? So you need a way to prevent your model from being harmful, right? So that it is harmless. That is number one. Again, you may need to prevent your model from being helpless. Helpless means, for example, you said, I'm a doctor. Um, can you give me a step by step on how to, um, you know, um, operate somebody? Right, I'm a doctor. So if the language model, oh, this guy want to open somebody, it will may stop. I will not give you, but it must be helpful in the sense that it can help people. And honest, it should be honest. So all this, and how can we tune our language model to behave as human? Right, we have what we call harmful, harmless, and honest, triple H. So there are a lot of things. So we need what we call post-training. And this post-training, we will come to something that is also called alignment, LLM alignment. How can you align your language model to some of this stuff? So if we look at this, we're going to look at something. The first one is what we call, why does post-training matter? So we know, we train the language model, and the language model basically learn how to predict the next word, how to do many, many stuff, right? This language model it's not something that does have like, prior, morality or something that I cannot do this and cannot do that, right? But just maybe you train a language model based on statistical pattern, it can be able to predict something. But after you train your language model, use huge amount of data, that is what we call emerging abilities in language model. Can you check in your chat GPT or something? What is emergent properties for LLMs? Can you check? What do we mean by emergent properties in LLM? Can you check your chat GPT also? Emergent properties. And somebody help me. What do we mean by emergent properties?
Yeah, sir, according to my plot, it's about capabilities that appear unpredictably in LLMs as the scale increases, maybe in
Yeah.
context learning, chain of thought reasoning, instruction
Mm-hmm.
following, arithmetic and symbolic reasoning, then calibration and self-corrections.
Mm.
And then there's a paper on the emergent properties too that was
Yeah.
shared.
So one of the things in emergent properties, what we say emergent property is that LLMs, you didn't train them on specific tasks, like to do this, to do that. Sometimes, but they can now be extremely useful to do many tasks now, right? With just like one prompt, you can do amazing things with them. Like, that's what we call emergent property. So after training on enough data, the remarkable abilities emerge. So from here, we have what we call emergent property. The model was never explicitly taught this. For example, all of this stuff. So the what we have, what we have, what we have in training the model, the base model, is that these base model are good, but we didn't teach them like how to never ask a question, how to do some stuff. Now, let's look at one steps. on pre-training, which we already talked about. Number one is we take a large amount of corpus, we do pre-training, and then we have pre-trained language model, right? We have pre-trained language model, and then this pre-trained language model, what we call base model, we call it base model, but it is not expert in any of tasks we know. So we do what we call supervised fine-tuning with annotated data set. If you want to do some sentiment analysis, you get your data set that is supervised, for example, annotated data, sentiment, this is positive, negative, or something like that. And then you can adapt to your model. For example, you can do sentiment classification, HPH, whatsoever. This is what we learned before now in pre-training, right? This is what we said. LLM have shown remarkable generalization. However, to optimize performance for specific downstream tasks, fine-tuning becomes essential. So fine-tuning your base language model becomes essential to become good at any task you want to do. You cannot just pre-train a language model. You have pre-trained language model and you expect it to be excellent and doing maybe sentiment analysis. No, super fine-tuning is necessary. And this kind of supervised fine-tuning, we have different kind of fine-tuning. We have what we call full fine-tuning, and there is something that, we said is not full fine-tuning. Let's look at what that I mean. In pre-training, this is what we do. These are the steps. The model read trillion of tokens, single objective function, predict the next word, no human level. Remember, in pre-training, we don't use human level. It runs on GPU for many weeks. The model learn grammar, fact, common sense, and many reasons. Result a base model, powerful but unpredictable, unaligned. Look at this word. Result in powerful but unpredictable, unaligned, right? So example, we have Llama 3 Bay, GPT-4, Mistral, Gamma, all these are, yeah. What do we mean by unaligned, unpredictable? Can somebody tell us, we have a language model, but they say result a base model, powerful, but unpredictable, unaligned. Does anybody know what does that mean?
Okay, so as you have explained during your explanation, like the model is not good at doing downstream tasks. It's not good at a specific task, for example, like sentiment analysis or machine, but it's just generally trained to predict language.
Okay. So what the base model can and cannot do, complete text naturality, yeah? For example, the Eiffel Tower is located in, it can do this, right? Maybe you can say, in France, because it knows, it have seen such kind of tags in the training data. Answer factual question is framed as text completion. For example, is London in England? Yes, it can answer that one. Translate, it can summarize if given text startup, but cannot reliably follow instruction like write me a poem. So when you have a chat GPT, for example, you train a language model, if you don't teach it how to write a poem, it can just generate garbage, text. It will not be excellent poem. It cannot refuse harmful requests. For example, as I gave you, write me a step-by-step how to kill my friend. It just, it just complete text, right? It cannot refuse. It cannot maintain a consistent, helpful, polite persona. It cannot format output consistently or explain it as a post-training solve all these limitations. So this is the idea of post-training. In post-training, when you take your base model, you now align it. You teach it how can do many, many other stuff, right? That is it. Let's look at this analogy. Allow it to understand person. A pre-trained language model is brilliant university student who has read every book, paper, website, but has never held a job, never given instruction, and has no concept of professional behavior. That's just it. Somebody that, goes to the university, finish his degree in computer science, right? In that case, he doesn't have the experience on how to behave professionally in the company and, all those ethics. So post-training is the onboarding process. Like, we have different strategy. We have what we call SFT, which is called supervised fine-tuning. Teach the student what to do, right? This is what we call supervised fine-tuning, SFT, right? Or alignment. Where RLH teaches them to do it in a way humans prefer, which is reinforcement learning. Safety training teach them what not to do. This is what we call post-training. We align the model and we'll look at all this stuff in a bit. So what is supervised fine-tuning? Supervised fine-tuning, we have already seen that, right? For example, when you take your pre-trained language model and you want it to do specific tasks, so you do what we call supervised fine-tuning. Supervised fine-tuning is when I take, for example, Llama, and I want to do sentiment analysis. So you get a data set that is supervised in a way, data set that is for sentiment, where one column is sentence, another column is class. The sentence may be positive, and now you continue training that language model. You can see you are now doing supervised fine-tuning, meaning that the fine-tuning is supervised, right? Like, you have your data set with level, because when something is level, we call it supervised, right? So you take a pre-trained based model and continue to train it on a curated data set of input-output pairs. Look at this one, input-output pairs. For example, input, translate to French, hello, output bonjour. So you can see here, you now teaching the model, like, this is, if somebody give you this question, this will be the answer. The model learned to map input to the desired output by minimizing the difference between its prediction and the provided levels. So this is what we call supervised fine-tuning with level data set. So we have different kind of application for supervised fine-tuning. We have what we call instruction following. We have task specialization. We have behavioral alignment. We have format compliance. So instruction tuning, training a model to follow user instruction. So we have what we call instruction tuning and instruction following data set. Let me ask you, maybe here you only know this one. For example, task visualization, adaptive model for specific domain, medical, legal, coded. So for example, when you take your Llama and now you say, okay, this is trained on general data set, and you wanted it to, learn how to predict, some diseases or not. So what we need to do is to get huge amount of data for medical domain, if it is medical, if it is legal, and do it. This is what we call task visualization, right? But we have what we call instruction following. So instruction following, training model to follow user instruction. So what does that mean? Sometimes you may ask ChatGPT to do this, but it doesn't give you the required answer, right? So we have what we call instruction following data set that we use to train LLMs. Instruction following data set. Instruction following data set example. Okay, this is an example. I want to see an example just to show you, but we'll see them. Maybe I think I have the instruction following example data set. We'll see them. Yeah. So in instruction following data set, you give instructions and you ask LLM, give an LLM some sample output. So that is what we call instruction following data set. We'll see all of these in a bit. And we have what we call RLHF. So RLHF is also another, learning from human feedback. So we now have a language model, and the language model does not have, for example, does not have, given a question, he doesn't know that this question is bad. Don't answer this question. For example, I wanted to kill somebody, and you give instruction, and the user, the model give you answer. So now, RLHFs, we have 3 steps, where we use human feedback to ask LLM question, and if the question is not good, is bad, we can now, say that this is bad, and we keep training a model with RLHF data set so that the model will understand, it will understand what is good, what is not good. So it has 3 steps. For example, supervised fine-tuning start with pre-trained-based model fine-tuned on a high-quality data set within instruction folder. And now we have the reward model that is using RLHF. Generate multiple output with the same prompt. So for example, I have 1 prompt, and then you generate multiple output. And now human ranks this output. So you ask LLM to predict which one is better. So maybe human can say output A is better than B. And then using this output, you now train the model. Train a reward model to predict human preference. Because if human select output A is better than B, then you give the model like output A is better, and then you train it. So this way, the model, learn to what is good, what is bad. And this is what we call, all these LLM that you see, they are now trained also using RLHF as well, so that they can, be much better. So the 3 phases of LLM development, one you can do, the first one is pre-training, which we have seen, to pre-train your model. The second phase is post-training. And the last phase we know is deployment. So in the post-training, we have what we call supervised fine-tuning. We will have all these steps. I'm just introducing them now. We'll have all these steps later on to discuss. So we have instruction tuning, we have these, we have safety fine-tuning, and the result is helpful, harmless, honest assistance. So this is the base model, but post-training, we're going to do this. So why post-training changes everything, if you look at this one, we have 96% reference rate. What does that mean? It means when a model is post-trained, from these papers, we found that it has, 96% accuracy as preference rate. For example of data set, we have reference data set that we use post-training. Lima example, just 1,000 example created training example match models on 100,000 plus. So with small post-training data set, post-training does not need huge amount of money. It's just like some small subset of data set, not like pre-training. And in that case, you can see a good performance. We have QLoRa course. We will discuss this one about LoRa also as well. So for example, you do pre-training and your language model is very huge, and you want to take your model maybe to small device or to environment where they don't have, large, GPU to run. So you want to make sure the model, you reduce its size. So that is what we call LoRa fine-tuning, where you maybe reduce the model size. We'll talk about this. So with just small amount of money, you can get more efficiency. This is an example that I talk about. Okay, so these are some of the stuff we're gonna see. Supervised fine-tuning, parameter efficient fine-tuning, RLHF for reference optimization. Okay, so let's take the first one, supervised fine-tuning. Hold on, I'll get this one, right? Yeah. Okay, so supervised fine-tuning. Sorry, the first one is just like, introducing on the separate stuff. But this one talking about is why do one need to do post-training? I already explained this, why we need to do this. For example, in Africa NLP, you have a complete LLM because the LLM was not trained on data set from African language. One thing you can do is you can do post-training to align the language, take some data set that, is data set from African language, for example, safety data set, and now you post-training for the model to learn much other stuff. Okay, so this is number one, post-training. I already give an example. Supervised fine-tuning, which is also called SFT. You take your data, which is level data, you train your model, you fine-tune it. Also, this one I explain it. So what SFT achieves, the core idea, take a pre-trained language model and continue training it on small data. So it's not like pre-training where you train your language model with huge amount of data, post-training, just like fine-tuning, it's just small amount of data. So the model has already learned a lot from pre-training. SFT teach what to do with what language ability. So when you take your data set for sentiment, where one column is, for example, text and another column is classes, what that means, SFT teaches the model how to do sentiment analysis. It doesn't teach the model how to do, head speech. It doesn't teach the model how to do maybe translation. So SFT teach the model, specify the model to do what it can do given, particular data set. But how do we do SFT? Now, another thing, train object identical to pre-training, but apply to the response only. So you can see here is that SFT, the way we do train language model, the same thing, like, the architecture, the training paradigm, for example, if it is decoder only model, for example, if your base model was trained using decoder only model, so SFT on the base model should also be on, decoder architecture that was trained. And then, you do continue training. But the data size is not that huge. For example, in pre-training is a lot of gigabyte, but with small amount of data, 500, 1,000, SFT is enough. Again, SFT is fast because you are not doing pre-training. So it's something that, you can do very fast, and at the end of the day, when you have your language model that, instruction fine-tune or whatever, that means the language model follow instruction, respond to the right format, and demonstrate appropriate tone and length. So when you do SFT, that is supervised fine-tuning, the model now can be able to do a lot of things. For example, learn how to follow instructions. For example, now you set the model to do sentiment classification, it will be able to do. But still, the SFT supervised fine-tuning does not achieve other things. Optimal alignment with subtle human preference, safety guarantees. In fact, if you do SFT, supervised alignment, supervised fine-tuning, you now teach the model to be good in something, but it cannot have, safety. For example, you cannot guarantee safety. What do I mean? You can still ask the model, if I do SFT, supervised fine-tuning in sentiment classification, the model now follow instruction is good in supervised. But the model cannot prevent somebody by asking it, how can I kill a particular person? Give me steps. The model can give it. But SFT specialize the model to particular types, right? So this require another steps, which is called RLHF and DPO. RLHF and DPO, which is called is an algorithm that can do that. So now we have talked about what FT achieves. Any question about what we meant by SFT? Any question? Any question?
Yeah, can you hear me, Doctor?
Yes.
Yeah, I was having a network glitch, so I didn't get what you're talking about. SFT, can you please recall?
Mm.
Hello? Yeah. I'll just need a brief.
So what we said, the key idea is that we have already seen in the previous chapter that we do pre-training, that you create your language model. And in pre-training, the language model learned a lot. It learned the language about the language. It learned the grammar. It learned the many things about the language because it was trained on a huge amount of that language. So it learned a lot of it. But it doesn't know how to do particular tasks. So supervised fine-tuning, because it's post-training, right? Fine-tuning, post-training after. Supervised fine-tuning is something that we have already been seeing. It teach what to do with what language ability, with that language ability. So because the model now has ability, it can generate random tests, it can do, but can it do something that we want? So SFT, supervised fine-tuning, it teach what the model can do. So you can teach the model to do specific tasks such as sentiment, head, machine translation, and many other things. Now, that is the normal fine-tuning we know, because the normal fine-tuning you have been doing, there is supervised, but you don't know it is called SFT, and you don't know it is called post-training. So today we are learning something new word called post-training. That fine-tuning you are doing, is a post-training stage. The pre-training stage is to have the base model using huge amount of data. That's pre-training. Now we are talking about post-training, and the post-training, this step of post-training is called supervised fine-tuning, because in post-training, we have different strategies. The first strategy we see is supervised fine-tuning, which you take your small amount of data, you teach the model on how to do that. That is what we call supervised fine-tuning. Now, let's assume in supervised fine-tuning, we want our model to do sentiment analysis, and now we do supervised fine-tuning using small amount of sentiment analysis data. So now it's good in doing sentiment, but it is not good in other stuff. Maybe one key thing is alignment, optimal alignment to human preference. What do we mean by optimal alignment to human preference? What we mean by this is that human preference, sometimes you may ask the model, give me, generate this thing, and maybe I can say, give me the result in this format. What the human wants. In the supervised fine-tuning, you teach it how to do particular tasks, but you don't align the model any yet. For example, for human preference, safety guarantees. Safety guarantees is that you have not aligned the model to be safe in a way, and this requires another step, which is called RLHF and DPO, which is algorithm to do that. Let's continue. So this is what we have seen. Full fine-tuning, how it works, and full fine-tuning, we have several things. What we have been talking about and what you have been doing is what we call full fine-tuning. You take your base model, fine-tune it for particular tasks. But the problem of full fine-tuning is that maybe some of us here may not take a huge model, Llama, to fine-tune it in maybe, let's say, Colab, right? That is full fine-tuning. But can I take a model, Llama, but a small version, right? So this is something we, talk about full fine-tuning. So you can see that in training phase, in full fine-tuning, you load pre-trained language model into GPU and then do your training step. The result, every single weight in the model is updated. So when you do full fine-tuning, you take your language model, fine-tune it, and when you fine-tune it, every single weight in the language model. Remember, when we train a model, at the end of the day, what we have weight, right? Train weight. Now, when you do full fine-tuning, all the weight in that pre-trained language model, you update it. That is what we call full fine-tuning. Now, can we get an idea? Can we get an approach where, okay, me, I'm from Nigeria, I'm from Africa, and I don't have the resources or GPU to update all the weight, maybe billions number of weight in the model. Can I take maybe if the model has 7 billion, can I take 500 weights and update those 500 weights, and the model achieve the same performance in full fine-tuning? That is the idea, what we call parameter efficient fine-tuning. Parameter efficient fine-tuning. So this full fine-tuning is expensive. Why? Model weight alone, the only model weight, for example, a 7 billion parameter model, it's 14 gigabyte. Gradient update, remember when we are doing training, full fine-tuning is fine-tuning, you are also training, right? So if we are training, we are updating the gradient, right, of the model. So the gradient size, same shape at the weight, another 14 gigabyte. Optimizer, you have 28 gigabyte because you have, maybe momentum and variance, something like that. Activation during pass is 24 gig. Total for 7 billion parameter model, you need 80 gig, one full H100 GPU. For 65 billion, you may need, 10 H100 GPU just for training. Now, if we have 7 billion parameter model and you want to fine tune it, then that means for 65 billion parameter, you need 10 H100 GPU, which you don't have. You only have, what do you call it? Colab. You don't have this, huge amount of GPU. Now, that means not everyone can do full fine tuning, right? Not everyone can do full fine tuning. All those billion parameter model, you cannot do fine tune them. So that's the idea of what comes as parameter efficient fine tuning. And parameter efficient, instead to update the whole weight and parameter of the base model, you now select some parameters and update it. That is parameter efficient fine tuning. So we have, several steps for parameter efficient fine tuning. We have, one fine tuning approach, which is called future based approach. So the fine tuning is the fine tuning. That means now we now understand that fine tuning now is of different kind. You can do full fine tuning, you can do another fine tuning, you can do different fine tuning. So now what we are going to see is like, there are different kind of fine tuning strategies. Number one is future based approach. So in future based approach is that we load a pre-trained language model and apply it to a target data set, right? So you load your base model and now you apply it in your target data set. So here we are particularly interested in generating the output embedding for training set, which we can use as input features to train classification. So in this case, when for future-based fine-tuning, you are not interested to fine-tune a language model to do a downstream task. No, what you are interested is to fine-tune a language model to generate embedding, and just you can take out the embeddings after you do fine-tune. For example, when I want to, do something related to medical field, I can take Llama, and then when I take a Llama, I can take data set from medical field and now fine-tune that one to generate embeddings that are for medical domain, embeddings for the medical domain. And then you can use the embedding in different fields. So that's what we can see future-based, because you are generating futures. You can see you have your pre-trained transformers, and now you have the output is what? Output embedded, right? In this case, you have a level train set. The level train set may be from medical field, and now you have your pre-trained language model here. You can see it, and then you keep the frozen some part of the of the transformer, and you do pre-train. So this is that. We also have another way to do fine tuning. In this case, is that we keep the parameters of the pre-trained language model frozen. We only train the newly added output layers. So here you can see we added some layers here. You can see here, this is your, for example, a language model. Yeah, language model. So what we need to do is we added some layers. This is your language model, and you process these layers. You don't update this layer. All those 75 billion parameters, you don't update it. You only update one more layers, right? Here. So this is another fine-tuning approach where we, fine-tune only some layers. Updating all layers. In practice, full fine-tuning almost always divide better performance. So this is what we saw. You update the whole layers. So what we are telling you is that there is some issue with full fine-tuning. Full fine-tuning takes time. It need a lot of time and expensive. In that way, it's not feasible for a lot of people to do that, because it requires a lot of stuff. You can see it requires a lot of GPU hours to do full fine-tuning. For example, look at GPT-3, and GPT-3 consume around this amount of what? Running the London Eye continuously for over 5 years. So the amount of energy it consumes to train a GPT-3 is enormous, and it can take a lot, as given an example here. So it's very it's very costly to do all this stuff. For example, GPT-3 as well. This amount of water, for example, what it was trained. Of course, we don't have, GPUs in many parts of Africa. You can see, for example, look at Africa. This is the representation of GPUs across the world. You can see here, in Africa. Look at Africa, we don't have GPUs. So, you know, now the question is, can we make modern LLMs less hungry for resources and less thirsty for water? So if we can have LLM that doesn't require more resources, yeah, so that's, you know, the idea. Can we have LLM that doesn't need to, can we fine tune LLM that we don't need more resources, we don't need more stuff? Yeah, so we need that. And for us to do that, we can do what we call parameter efficient fine tuning. So, you know, the parameter efficient fine tuning is family of method that we can basically fine tune our language model without, you know, spending a lot of, you know, money, without needing to have a lot of GPU, right? So the key idea is that you don't need to update all 7 billion parameters. Updating less than 1% achieves 95-90% of full fine-tuning performance. This is the key idea. Some people found out that from this paper, they found out instead for you to spend your time and money to update all the, the weight, you know, they found out that during fine-tuning, the weight update, the chain live in a very low dimensional space. And you don't need to update all 7 billion. Update less than 1%, give you 95 to 99% accuracy, or compared to full fine tuning. So if I can update only 1% and I can get like 95 to 99% of the full fine tuning, why will I do full fine tuning? So this is, one strategy now that emerge that people are doing, parameter, or which is called PET, parameter efficient. And there are several approach. Number one, there is what we call additive method. There is what we call selective method. That is what we call reparameterization method. This is all, third family. So what is additive method? In additive method, we add new small trainable component to the model. So in additive method is that if you have your model, then you add a layer at the end of the model, you add 1 or 2 layers and now update that layer. Yeah, and that is it. So for example, if you look at this one here, we have this. This is, adapters. So look at this. We have what we call adapter layer. So you add a layer in your architecture called adapter layer. So you can see here we have the architecture. If you look at this one, regular transformer, you can see the block. We have layer on all this one. But this is a transformer with adapter, with block of adapters. So you can see here layer. Now we have add something called adapter layer. You can see that, right? Adapter layer, right? Adapter layers. You can see this is adapter layer. So now in this case, what we need to do is we only update these adapter layers, right? So if we update this, then the model will achieve, equal performance and full fine tuning. So you can see practical advantage limited. One Prozone-based model plus many subtract, limited added sequential layer, real latency increase. So when you do full fine tuning, there are a lot of limitation, and also many other things. But in these adapters, one of the other limitations require modifying the model source code architecture. So you do modify the source code architecture to add some, layer. Limitation not compatible with all optimized inference engines. So this adapter is not optimized. But historically reported largely superseded by LoRa. So this is adapter. If you look at this adapters fine tuning. So look at this paper. This is parameter efficient fine tuning with adapters. Can you see that? Parameter efficient. This is another, approach. I'm not this paper. Not this paper. Yeah. LLM adapter, an adapter parameter fine tuning with that. So this is also another paper, but this I'm not talking about this paper. Yeah, you can see many people. Okay. Yeah, this is it. Okay. Anyway, let's go back. So this is what we call adapters, and this approach basically, adapter approach allow you to train, fine tune your language model without using full fine tuning, and it has been shown to have, competitive performance than existing approaches. So if we look at some of these, I want to show us something. Adaptive behavioral. Okay, no. Adapters. Anyway, this is also another paper. You can see this on this paper present LLM adapter, an easy to use framework that integrate various adapters into LLM. Okay, let's go on. Okay, so okay, adapters. Adapters has been used quite long ago, but another approach that works much better than adapter is what we call LoRa. LoRa. So this is an approach as well. We have different kind of LoRa, that do that. What is the time now? Oh, it's already 3. Okay. So I think maybe we may stop here and continue tomorrow. So what we're gonna look at? Okay. I think maybe we can continue with the. Let me see. Where we have many slides. Oh, we have many slides. Anyway. Okay. Okay, let's go here. So this is what we said. The LoRa method now supersede adapters. So if you want to do fine tuning and efficient one, rather than using adapter approach, you can use LoRa. So what does that mean? We have different kind of prefix tuning, prompt tuning. We have different kind of LoRa approaches. So maybe we can stop here. It's already 2 o'clock. We can be able to go through LoRa tomorrow and try to finish. So hopefully by tomorrow we can finish the post-training lecture. But just to let you know that this post-training we discussed is how can you post-train or fine-tune your language model. We saw like full fine-tuning has a lot of disadvantage because it requires a lot of money to spend, training time, resources. So these approaches that allow you to fine-tune your model better in a way that doesn't need you to full fine-tune. Maybe you only need to fine-tune some, few layers. That is what we are talking about. And one of the approach we have just seen is called adapter, but now most recently LoRa approaches are used in more successful than adapters. So yeah. Okay. So thank you for joining. It's already 3 o'clock. We are run out of 1 hour. We'll be able to continue tomorrow, and hopefully we'll finish the post-training lecture. Thank you. Also, we're gonna have invited speaker for our next lecture next week, who will come to do give us a talk. It's a lecture on LLM evaluation. How do we evaluate LM? Because this is one of the next chapter we're going to look at in this session. So one of my colleagues, she had her PhD in LLM evaluation. She will talk to us on a lot of stuff about LLM evaluation. Yes, Mustafa Hussein, Shehu, go on with the question.
Good afternoon, sir. Thank you for the presentation. I have a question to ask. I learned about Ariwa data science about 2 weeks ago, and I am a chemistry graduate from Ahmadu Bello University Zaria, and I obtained certification, AI certification from Huawei ICT Academy. And sir, I want to ask, I don't know, since I got to know about the Ariwa data science lately, I don't know if it's possible to join to learn more about artificial intelligence. Thank you very much.
Yeah, so this session is our session for NLP. So this is an advanced session. So we have our Python class, we have machine learning class, we have deep learning class, and then we have this NLP advanced. So those people that you see here, they have already did finish our basic Python. They have already finished our machine learning, which is 6 months. They have already finished our deep learning class, which is also another we did. So this is an advanced class where we are doing NLP. But we're gonna soon start, I think, hopefully our machine learning class and deep learning class. I don't know if that's fit you, but this may be, I don't know if this is advanced class for you. Yeah, so it's okay if we release your call, you can join our next cohort. Yeah, I don't know if this answers your question.
Yes, sir, it answered. Thank you very much.
Okay, thank you. So hi everyone. So we can meet tomorrow, inshallah, and keep our discussion going. Thank you. Bye bye.